Good morning. My name is Amela Ajanovic. I'm working at the Energy Economics Group at the Vienna University of Technology, and it's my great pleasure to chair this dual plenary session on the future of transport and electricity systems. As you know, due to the changes in the transport as well as electricity systems, they are facing many new challenges. We can notice increasing use of renewable energy sources, digitalization, decentralization, as well as electrification. Due to the increasing electrification of mobility, transport and electricity sectors are becoming more and more connected. In the past, in the 19th and 20th century, in the transport sector was car-oriented, mostly based on the fossil fuels. Now, in 21st century, we have new solutions. We have new alternative fuels, alternative automotive technologies. However, how fast these new developments will take off depends on the boundary conditions set by policymakers as well as consumers' willingness to adopt new technologies and services. However, for a future, we need reliable, economically affordable and environmentally sustainable energy system. We need to make some changes, and some issues related to the future transport electricity systems will be discussed in these sessions by three excellent speakers. Ben Schlesinger from University of Maryland, Reinhard Haas, Vienna University of Technology, and Richard Green from Imperial College London. So I will now ask our first speaker, Ben Schlesinger, for his presentation. He will focus on the transport issues. Ben, the floor is yours.
Good morning, everyone. There are a few extra seats in the back if someone wants to take them. It's really a delight to be in this beautiful city, and I thank Reinhard and the other organizers for allowing me to participate. This is truly one of the beautiful cities, and the weather has proven it as well. So I can't see my slides unless I step basically out the window. So I may do this. What I'd like to do is advance the slide. The monitor I'm using is not linked with the presentation, so I'm hoping that I'll be on the same slide that you are on. Okay. Right. So a couple of things to cover. This is kind of a general piece that focuses on kind of the battle of revolutions. There are a number of revolutions, but in the energy field, from where we sit, at least in the United States, there are two really important revolutions taking place. And we want to speak about these, batteries and natural gas, and how these interact, and where the flashpoints are. For some time, I've been concerned about natural gas markets, a lot of years, and this kind of points to a different direction that causes me some concern. I used to date this slide and say 30 years, 35 years. Now I just say a lot of decades of gas advisory services. My day job is really in the natural gas business. Are we right? Thank you. This doesn't really happen. What's the best way to point it? Back here or at the slides? My day job's in natural gas. This is actually one of the first times I've ever been to a conference and been across from the natural gas panel where I'm more or less at home. So I don't plan to leave this panel. This is getting very interesting, and in some ways more interesting. But don't tell my colleagues in the natural gas business that. But our work really focuses on gas midstream, pipeline, advisory services, gas storage, a number of projects really globally. Lately, a good deal of work in the LNG, liquefied natural gas space on behalf of buyers in the United States and advising them on how the market works and what are the right pipelines, what do they cost, and will they ever be approved. So, of course, our big revolution is shale gas, which is now up to 60% of U.S. production. It always makes me laugh when people say, stop fracking. If we were to do that, we would be somewhat in a mess. It also undercuts other exploration and production. There was once a chairman of the U.S. Federal Energy Regulatory Commission named Martha Hesse. And Martha had a rule that if you ever used abbreviations in a meeting with her, she would force you to pay a quarter, 25 cents, and put it in a jar. So, this is my first 25-cent crime here. Exploration and production. The really interesting story of this is, of course, the Appalachian gas, which takes in the enormous Marcellus field, the Utica field, Devonian shales, and some other co-located shales, which are together really producing more than the Russians expect Bovanenko to produce, which is the largest field in Yamal. This thing is on scale of Yamal. It is already outproducing Qatar, and but it's not in the Arctic. It's it's about 200 miles from my house in Bethesda, Maryland. It's in the suburbs of Pittsburgh. Unbelievable. This field is basically now flowing to Texas and Louisiana, which is a real change for the American gas network. The pipes have had to be reversed to move this gas south. It'll also support the first round of LNG projects to a great extent. Other fields are also important, and they're shown as well. So the problem is, what do we do with this gas? We have too much of it. Markets are terribly imbalanced. And, a good demonstration of imbalance is the flattening of the production for the past year and a half, or 2 years. The fact that production flattened does not mean that the field is running out. It means that we don't know where to put the gas, so we've stopped drilling almost completely. I visited one field after our USAE conference in Pittsburgh 2 years ago. The field is a flat top mountain, about 3 acres, about a hectare, I guess, 1 hectare, producing 100 million BTU a day, 1,000 MMBTUs. This is a lot of gas. It's about the equivalent of a nuclear plant. The water towers are in place, but there's no fracking taking place. It's unnecessary. It was fracked a year earlier, and it keeps flowing. The pipelines come to you. When you have this much gas, they come to you. You don't have to worry about going to the pipeline. They'll find you. But the markets are imbalanced, and the price, of course, has been about $1 or $1.50, where it sits roughly now. $1 or $1.50 is not enough to make money on, and so drilling is stopped. The markets are imbalanced. We're looking for markets. Chemical plants, great use of gas as well as the liquids. Enormous amount of construction taking place between New Orleans and Houston. God, hope so. Hope that construction's still going on. Enormous amount of manufacturing. In addition, about 70 MTPA of approved LNG projects that are under construction, and another roughly 50 MTPA, million tons per annum, approved and awaiting final investment decision. But of course, there's an enormous number of projects behind these. Everyone wants to build an LNG terminal now, and the fate of these terminals, the next round of terminals, which are uncontracted, really depends on the market as much as anything. So the surplus gas, of course, replacing coal, and that's great. The United States was on a coal-fired power plant building binge when I was a kid. and even before I was born. During the 40s and 50s, we were building coal plant after coal plant. Great idea. And now these plants are kind of aging. So our situation really is this, that gas and coal are competing very closely in terms of price. But the coal plants are very inefficient. So new gas-fired power plants are much more efficient. And so even if you miss the price point, you're really there because the plant's so much more efficient. It's kind of an unfair competition between new, efficient gas and old, inefficient coal. So the coal plants are being replaced, regardless of regulation or deregulation. This is happening because of market forces. You know, as a result, gas has pretty much picked off coal as the largest fuel used for power generation in the United States. But you'll see renewables are rising as well. So the net sum of all of this is that carbon emissions from the electric power gen sector are dropping, although I see there's a little stall this year, a slight stall. But we suspect this would continue to go down as, you know, as more coal is replaced and more renewables come into play. What else to do with all this gas? Well, we can match renewables. The uncertainty of renewable production is a great potential market for natural gas. It's an existing market. Here's a shot from Kevin Forbes' presentation a couple of years ago showing a windy day in Texas, a windy month in Texas with enormous variations even within days. So what we do is basically use either LNG or pipeline gas to try to offset this. It's a little tough with pipeline gas because pipelines are very long and they've got to be managed. LNG is a lot more appropriate for this kind of balancing. The Spanish do it. The LNG terminals and the gas-fired combined cycle combustion turbines are co-located. They're put together. So the LNG can be put right into the power plant, not bother with a pipeline, and the power can be turned on pretty quickly to balance wind. This is a tank of LNG in Maryland. We have a large number of these tanks in the U.S. Hey, what about cars? You know, that's nice. Cars and trucks, it's good market. Gas is clean. So I'm kind of a poster child for this. I drove 7 years in 2 different natural gas cars that I converted. My own car, my wife is pretty upset about that, but they both ran fine. This is one that Chrysler was going to produce, a natural gas powered Dodge, very fast car, using the latest flat tank system, so they have a big trunk and goes 300 miles. Great, except no, not great. Nobody produced this car. People just stopped producing them. I used to be on the phone with Chrysler and they said, you know, come on, tell your gas utility friends to buy more of these natural gas Chryslers we have. And so first off, no one even knows you have them. You don't advertise. So, well, we don't have an advertising budget, you know, hang up. The manufacturers were never interested in this. We can talk more in the Q&A. But for larger vehicles, it has caught on well. Here's a Los Angeles city bus. Every single bus in the city of Los Angeles runs on natural gas, without exception. Large trucks, here's Westport Cummins, very long distance LNG powered truck. But the action has really swung more to electric vehicles. And when you think about it, in many of the regions in the United States, with all of this gas burning for electricity, natural gas sets the marginal fuel. Richard will explain this more and better than I can, but the marginal fuel for power gen is natural gas. If you flick on the lights, it causes natural gas to be burned. That's fine, and that means that you know, our Tesla here is actually a natural gas vehicle. It's just a little more efficient, and it comes through a different fuel chain. Okay, part 2, competitiveness. Where are we going with all this? So there's a rule of technology. I'm speaking as an, you know, I guess registered engineer in California. Technology and production are what creates change in this energy business, and I think we'll talk about it all week, and we've been talking about it in past conferences. Technology and production, massive production, massive production. There was once a Reagan appointee and his transition team many years ago named Michael Halibutty, a driller from Oklahoma. And Halibutty had 3 solutions to the energy problems: produce, produce, produce. Interesting. We do this and we increase the productivity enormously through 1,000 little improvements, not just one improvement or 2 improvements. And solar energy, and Richard's got a much better slide than I do on this one's a little dated. Same basic idea: produce, produce. In China, in the United States, and elsewhere, through 1,000 little improvements, the cost of solar panels has come right down, photovoltaic, to conventional energy. And now batteries. We're entering a phase where we're produce batteries. Well, what do we need all these batteries for? There's only not even 1 million electric vehicles. This slide is really dated. We'll talk a little bit more about how quickly battery costs come down and what's driving that. So just one last reminder on natural gas. We're going to talk about gas. Gas is used as a peaking fuel, open cycle gas turbines. Open cycle gas turbines, very relatively inexpensive power plants that burn gas. Some are there are piston engines, which are shown as well. These are a plot of what has met peaking needs in the United States. These plants may burn just 500-600 hours a year, anywhere from 200 to 1,000. But it's a market. And it's kind of experiencing issues. Right now, the flashpoint for this market is in, nice Los Angeles, Hollywood. What's your dream? Well, maybe it's a bad dream for the gas industry. So this is the sequence of things that's happening. Rising use of solar energy. California is second only to Germany as a, quote, country. For us, it's a quote country. It's second to Germany in terms of the incidence of solar energy, the use of solar energy installations. So with more and more solar use, this intensifies the evening power supply ramp up. Every evening, more and more, people have called this the duck curve, and I'll show you the duck curve in a second. But when the sun goes down, image the sound of 1,000 lawnmowers starting up, 1,000 cars. This is 1,000, power plants, many power plants starting up fast. This forces, since they're all gas, this forces a real extensive demand for power generation, which stresses the region's infrastructure terribly. The infrastructure in Southern California is blessed with an enormous gas infrastructure, a lot of pipelines and a lot of storage. The largest underground storage field west of the Mississippi River sits right north of LA, Los Angeles, called Aliso Canyon. And so that's how the gas industry meets its peaks, its summer peaks. You can see gas is the majority of fuel used for gen in California by far. The problem is, about 1.5 years ago, a major leak was discovered coming out of Aliso Canyon. And as a result, Aliso Canyon was shut for safety purposes. Wow, this really took a big hole out of the infrastructure availability for natural gas-fired power plants to come on quickly. The region's electric utilities, are now facing peak period shortages. One of our clients is Los Angeles Department of Water and Power, and I can tell you they are very nervous about this. And this has what has underlain a fast turn to battery demand. One way to do this, place the batteries, not necessarily where the power plants are, but put them in the neighborhoods near the transformers, deep in the distribution system. And so a massive order of new batteries has been made, and of course the largest battery factory in the world is about 400 miles north of Los Angeles, outside of Reno, Nevada, the so-called Tesla Gigafactory. Tesla was the first to install a battery installation, but others have followed. There are LG batteries going there. There's every make and manufacturer of lithium-ion battery being placed in the Los Angeles basin. So what's the effect of that? Well, massive production, produce. This is a huge new demand for lithium-ion batteries that is lowering the cost, enormously. And here's this duck curve showing the ramp up that is required in the evening as the sun goes down. By 2020, Southern California Edison estimates they're going to need 13 gigawatts of electric power to suddenly be brought on over about a couple of hour period. I don't think the gas system can handle that. That's going to have to come from batteries. More and more, there's a realization. So what is production doing to the cost of batteries? This is a study that National Renewable Energy Lab did a couple of years ago, looking at costs, or really the value of electricity storage in different markets. The colors represent the range. So for example, and ARB is the arbitrage, essentially the high cost to low cost daily production of electricity in PJM, the Pennsylvania Jersey market. This would be like $50 in Martha Hesse's quarter jar. Sorry about that. Pennsylvania, Jersey, Maryland, electricity storage is worth a little over $100 a kilowatt hour. Another market is the regulation market. So in New York State, the New York State Independent System Operator, NYISO, the regulation market, it's actually worth quite a bit more, maybe up to $200, anywhere from $150 to $250 is the willingness. This is essentially the value of electricity storage, value of a battery, and the others refer to other regions. So where are we? Well, Tesla's first Model S, happy owner, 2012. I did show part of this in Bergen last year, but of course we've got an update for that. Not quite. The battery was really $350 per kilowatt hour, and only in a pretty extreme situation. I think there's a switch of labels. The New York ISO, the regulation market, maybe not. But time passes and production increases. Whoops. The 2016 Tesla, last year, my second one, the battery, and we got this confirmed in Bergen by the Tesla representative on our panel, that the cost of the battery is $250 per kilowatt hour. Pretty cool. And I suspect the 2018 Chevrolet Bolt, which is here known as the Ampera, is essentially about the same cost, about $250, maybe less. But as I started to show, God bless it, this thing doesn't want to go. Yeah, the Tesla Model 3 is really looking like it's going to be under $150 because of massive production. It's already coming in at a very low, comparatively low price compared to the other Teslas. So maybe by 2020, Volkswagen and others who are planning electric vehicles in a serious way will be down under 150. Well, where are we there? Well, we're still kind of not there with the arbitrage load. We are there with the regulation load, So it's already, and that's part of what, that's part of what the useful batteries will be. What does all this mean? What does it all have to do with gas demand? Well, it has a lot to do with gas demand. The most vulnerable markets are going to get hit first, and that's actually the automobiles, compressed natural gas cars. In my view, having driven them for 7 years and electric vehicles for 5 years, I really believe that's it. We're not going to have a lot more compressed natural gas cars. The manufacturers never wanted it, and now they're falling over themselves to build electric cars. Maybe the large-scale vehicles, I think, will survive this. Peak shaving, we've discussed. Offsetting wind, this still might be okay market in some areas, but as that gets as that market gets picked off, what's the next market? Well, it's probably not a gas market; it's probably a petroleum market. What we see as a threat really to the gasoline vehicle, if the batteries get really down to the $50 to $100 range, which is where they're going. Schlesinger, you're nuts. We have 250 million cars in the United States. What do we have? Not even 1 million electric vehicles, almost 2 billion cars. How's this going to happen? The past tells us a little bit. in the late 1800s, there were horses were the means of transportation. There was a growing horse population. This is Department of Agriculture data. As the as the economy was improving in the United States, we had more and more horses, and then suddenly, no more horses, lots of cars. Someone else showed a picture of the Easter parade in Manhattan with all horses in 1900, and then in the year 1913, all electric cars, no more horses. I don't know if it can be done over 10 years, but who knows? People still like their horses, and of course, people will still like their gasoline cars. I'm going to have to skip some. I'm starting to run low, but the transportation sector in the U.S., unfortunately, is still. There we go. Yeah, transportation sector is actually getting worse right now in terms of carbon, not better in the United States. So we've got our work cut out for us. This, when you take a closer look, this is kind of a paradigm: high battery costs versus low fuel and high fuel. Europe is probably in the upper right. The United States is probably in the upper left. But in either case, we don't have the breakthrough. But as we move down to lower battery costs, depending on how oil and gas prices are, we're going to see very quick development. I think we're probably in the U.S. headed toward the lower left. This is what California's regulators anticipate. So there's a measured, quick uptake of batteries, but primarily for the electric and initially for electric and then vehicles. But of course, Tesla's world would be, high fuel prices, low battery prices, and then it all happens fast. And it would. So I think supplies are going to stay long for 2 decades. In my view, we're not going to see, the gas, supply drop, at least not in North America. We'll keep replacing coal plants until we don't have any coal plants to replace. We're done replacing coal plants in another 5 years in the United States with gas. We'll run out of coal. When there's no more coal to replace, the idea was to replace gasoline in vehicles, but I don't think that's going to happen for natural gas. I really don't. And so we've got enormous infrastructure. I think we're going to continue to see some growth, but I think we're going to see electric vehicles probably grow into the millions. So that's kind of it. I'll be happy to discuss this. I apologize for running over a little bit. I'm winding this up on mine instead of yours. So thank you very much.
Thank you very much for your presentation. Do you have some clarification questions now? We will have discussion also later. Is there any question?
It's totally clear.
If not, just one, please.
Just one question on the slide on battery revenues. Was that per annum figures or over the lifetime of the battery?
I believe it was over the life of the equipment, yeah. $250. I really have to check. Actually, I think it was an overnight capital cost. That's the way I've been treating it. So when I reviewed the paper, I believe it's an overnight capital cost. Here's what a battery costs that would solve this. The load would be the demand would be continual. So the overnight capital cost of $200 an hour would serve a load that continues on an annual basis. Is that clear?
Yeah.
Thank you very much. Now we will move to our next speaker, Reinhard Haas.
Good morning. I think I know almost all of you. I will not introduce myself further. I will today take the opportunity to share with you our ideas on the new thinking which takes place in the electricity markets compared to the old one. I will shortly introduce the motivation. I will present our major method of approach, show the basics on how variable renewables impact prices in the electricity markets, explain the core problems of capacity payments, explain the role of flexibility, sector coupling, balancing groups. I will shortly address the question of how long will we go to subsidize renewables, and conclusions will complete my presentation. There are 4 major points with respect to motivation. You know, we have the climate change problem and the Paris agreements, which has to be met. In Europe, still we have targets for renewables in all sectors. We strive in general for more competition and transparency in the especially electricity market. And a final major issue is that it is not possible to squeeze variable renewables into the system by violence. We have to strive for system integration, and we have to strive for proper financial incentives to manage it. For the last, let's say, 20, 30 years, we can see the development of different energy carriers in electricity generation in Europe in this figure. And I remember in former times we talked about alternative energy when we spoke about renewable, but today we have renewables as the mainstream energy carrier. Since 2013, renewables contribute the largest quantities to electricity generation in the EU 28. And for a long time, the thinking in electricity industries was and is in many countries still that the core part of the system is the generator. Large generators, powerful generators with huge plants were the center, the core of the electricity system. And it was actually a one-way system. From the generator to the grid, to the supplier, and finally the customer, to meet demand. Actually, the customer was usually not mentioned. We just spoke about demand. And there was some flexibility on the generation side with respect to, let's say, large hydro storages. The core objective of my presentation is to identify the major boundary conditions to integrate even higher shares of renewables, of variable renewables, into the electricity system. And in this context, it is very important that despite in many countries we still have, let's say, the old thinking, our reflections apply in principle to every electricity system in the world. And I would like to add, it is based on an electricity economic point of view. That is to say, I do not go into technical details of grid and other aspects. Our method of approach is
Point it right at the slide.
is identification of hourly residual load over a year for various scenarios of large quantities. And we apply a fundamental approach, that is to say, we calculate hourly residual loads and the corresponding electricity prices, and finally we also include the flexibility measures and alter the price calculation. This goes ahead with the expectations that in day-ahead electricity markets we have the expectation that prices are equal to short-term marginal costs, and of course short-term marginal costs are the fuel costs. This was the thinking that was initiated due to high depreciated excess capacities at the beginning of liberalization. Now we look how the variable renewables impact this system, impact the electricity system and the markets. It's a simple example. Here you see a typical merit order curve, supply curve, without variable renewables or without, in this case, photovoltaics. And we shift the curve to the right, or not. So, where should I put this direction, or?
I believe it's the battery.
Did you bring some with you, Ben? What can we do now? Okay, maybe. Which battery do you have? One, two. Is it? That's too small. Okay. Is there any other battery expert in the room? Let's try it. So let's try it this way. We have photovoltaics shifting the supply curve to the right, and this leads to the situation that we will have another different intersection point of the price with the system. And this was for 1 hour. We have lower prices due to the variable renewables. And here in this figure, you can see the same effect over a week. We have seen it several times here in this conference already. We have sometimes over this week where renewable generation is higher than demand, and others where we have renewable generation lower. And in these points of time, we have to, as Ben explained before, look for some storage opportunities. However, this situation, the picture I have shown, is kind of the approach of new thinking, because we do not start with baseload, we start with available renewable sources, and finally the difference between demand and supply provides the so-called residual load. Again, in this context, baseload is dead, residual load is load minus non-flexible generation. Some points of time we have excess electricity, at other points of time we have undercoverage. And now the question is, how can we provide incentives? And incentives can be provided mainly by the correct price signals. And these price signals are shown now in this figure for the residual load curve I have shown before. We have currently in most countries rather low average prices for electricity, maybe in the magnitude of about 3 cents, but we can see that in principle at different points of time we have high prices, so-called scarcity prices, and at other points of time we have low, even sometimes negative prices. This leads to the fact that we will have finally a rather new high price spread in a future with high shares of variable renewables, and these new price spreads should provide the incentives for the storage and for other new flexible solutions. Just to show how high these prices can be, in Germany they were limited or accepted at maybe 3,000 euro per megawatt hour, but what we could see this year when we had the so-called kalte Dunkelflaute in Germany, which is something as a cold dark lull, the price, the maximum price in this period was actually only about 85 euro per megawatt hour, which is what I think very, very moderate and does not lead to this extended suggestions provided before. Now we classify the residual load over a year. I show it here for 2 years. This is from, let's say, Central Europe, from Western Europe, 2013 versus 2016. 30 with high shares of variables. And we can see that in 2030, the curve is much steeper than in the year 2013. That is to say, due to the increase of the variable renewables. In this example, we have a higher surplus in the lower right corner than before. Now we try to, let's say, explain or look at the major features of this graphics, and we have the right circle on the top left, and this red circle is the critical problem. We have to think how to cover the electricity in this corner, how to cover it at times of the so-called cold dark lull. And in principle, there are two possibilities. We have two extreme positions actually, and the first one is we can do it by a regulated capacity market with short-term marginal cost pricing, or we can do it by competition between supply and demand-side technologies and behavior. And this includes storage, grid, and other flexibility options. And we have to ensure that we have correct scarcity pricing signals. First option are the capacity payments. I think with capacity payments along go the following problems. The capacity payments distort the energy-only market, and they lead to low to wrong price signals for all other options. Price peaks at times of scarce resource should revive actually the market and lead to effective competition, and we should strive to retain the system resource adequacy by ensuring the correct price signals without capacity payments paid by, let's say, the state. And to explain it more in detail, we look at the cost duration curve. And this is shown here for the hours over a year in euro per megawatt hours. And the generators will stay in the market if their revenues, the sum of electricity price times quantity, is, as shown here in this figure, higher than the costs over this year, the capital and the operation and maintenance costs. In the figure you can see sum of T1 to N is this period, and over this period of the higher prices we need the correct price signals to have the generators staying in this market. So given this price pattern showing excess and scarcity prices, it would be attractive for sufficient numbers to stay in the market, and this is then called a so-called revised energy-only market. In practice, we have a considerable number of flexibility measures, and these are shown here in this figure. We have flexible generation, storage, grid extension, smart grids, demand response, demand-side management as the major ones. And in the part of the area I've shown you, we have the following effects finally. We can cover a specific quantity by means of extension of transmission grid, which flattens the demand curve and flattens the supply one. This leads to a first reduction of the load, and next is in this figure we have the opportunities that very high prices exist, and we will have load reduction due to the demand response due to these prices. Then we have a specific area with demand-side management measures, and technical demand-side management is well known since at least more than 50 years by means, for example, of cycling for electric heating or electric water heating. Finally, the most important part here are the capacities, the backup capacities from the flexible power plants. They are shown here in this figure, and this is actually the quantity needed given we have also flexibility measures. In addition, we have storage, but storage at the point of highest demand are usually empty. So here we have finally a capacity without any insured payments, just brought about by the market. Next, storing every peak. We have already heard from Ben the relevance, importance of storage. And what is important is that the high excess capacity exists only at very few hours. And then the question is whether it makes sense to really store every peak or to do something like shedding, for example, of wind power plants. However, over the year, we will not come to the equilibrium with battery storage. We have in summer times higher production, for example, due to PV, and we need something like a long-term storage, which is not represented by a battery. And now we come to the issue of sector coupling, sector integration. The idea is that in times of surplus generation, how will we use excess capacity in a useful, meaningful way? This is first possible in the, let's say, heating and cooling sector, and second in the transport sector. Currently, I would say there exist many vague and simplified suggestions which are not convincing long-term solutions. For example, we have central approaches and decentral ones. Central are usually the P2X approaches, and decentral, for example, electric vehicles or heat pumps for heating. However, we have the problem how to fit the use with time of surplus. So if we have surplus of photovoltaic electricity, we cannot use it for heating in wintertime. And one example has already been shown by my colleague Amela yesterday. It goes in the direction that we have direct use in electric vehicles, and we have indirect use here at the end in the fuel cell cars. With respect to the system of the electricity market, we have to consider that we have not just one market, we have at least the components as shown here in this figure. We have the long-term market which dominates, and then we have short-term day-ahead and intraday markets. In addition, we have control power balancing energy. We focus now just on the short-term market because here we expect the proper price signals. This was the wrong sign. And the idea is that with respect to the day-ahead and intraday market, we think about balancing groups, balancing zones. We have them in Austria, we have them in Germany, and these balancing groups are entities in control areas, and they have to ensure that at every moment of time, demand and supply is balanced. For example, municipal of utility, of Vienna, of Dresden, of Helsinki, of every other county, of every other city may be such a balancing group. So the balancing group has, as can be seen here, generators, it has imports, it has exports, and finally we have customers. And we have to ensure that there is a balance between these different participants. And it is important to note that the possibilities to meet these targets are own generation, storage, flexibility, trading, actually all possible measures. Finally, we have to state that every difference in the balance of this balancing group causes high costs, causes tremendous high costs, and this should be an incentive for every balancing group or supplier to keep it as low as possible. Finally, I would like to go to the decentralized application and shortly discuss whether the time for subsidies for renewables is over. Of course, in this context, it is very important whether we have a price on CO2 or not. Higher CO2 price would make it much easier to come along without subsidies. Here we have photovoltaic situation in Germany. Blue curve represents costs. Green curve represents the household electricity prices. And we have in Germany since about 2012 something like grid parity. which means that we have prices of generation are lower than household electricity prices. And if this situation prevails, we just have to look how many kilowatt hours we fit into the grid and how many we take off the grid. And here you have on the left-hand side the savings and revenues, the grid parity term, which means own consumption times household price, and we have the feed-in price times energy fed into the grid, and this has to be higher than the costs, the annuity of the capital costs. So here we have the situation for today in practice, whether subsidies are still necessary, clearly defined. In addition, own consumption depends also on storage. So the lower line shows just electricity from photovoltaics. Green curve is photovoltaics plus battery, as shown by Ben before. And we have the red curve, PV plus a heat storage. This leads me to the issue of new thinking. In the past, I have shown generator was in the center. Here we have different types of generators in this new system, and they will feed electricity into the grid and transport it maybe to a storage, to the, finally, as I've shown, the balancing group, the supplier. We bring it further to the so-called prosumagers, a definition by Richard Green, who gives the next presentation. We have a lot of flexibility options. We have demand side, on the prosumers side, generation, as well as storage. So this is maybe the solution for the future. And in addition, I would like to show this graph regarding the so-called possibilities for tenants in a multifamily dwelling. We have balancing group suppliers and the old system with meter, shown here in this figure. Now let's add a PV system on the roof of this building. And this allows, in addition, to the tenants to contract PV electricity. So here we have contracted electricity. But next comes now the idea of the blockchain, and the idea of the blockchain is that behind the meter electricity exchange between different customers and appliances is possible. And in England there are also ideas for peer-to-peer, where the customer finally really can identify where from his electricity comes, for example, from a solar farm, from a hydropower plant, from a wind farm. And this leads to my major conclusions, which are, first, that a sustainable electricity system is dependent on an integration of a broad technology portfolio and demand-side options. We have the advantage of larger markets because they have more balanced demand and supply. Very, very important are, aside from CO2 prices, correct price signals, at least in the day ahead and intraday market. Most urgent is to exhaust the full creativity for flexibility of all market participants, including the decentralized PV systems. Capacity payments, from our point of view, just distort the system towards more conventional and less renewable energy capacity. And I think what is very important is that the new key player is close to the demand side, the balancing group, or the supplier, and no more the generator. Thank you for your attention.
Thank you very much for your presentation. I'm sorry for the technical
Yeah, but we
problems.
have to solve it now for the next presentation.
Yes. Do you have some clarification questions, or if not, we will move to the next presentation, which is connected to this one, and our next speaker is Reinhard Green.
We just changed it.
Okay. Okay, well, thank you. Thank you. Well, I'll talk for a moment before I need to move the slide anyway, but No, it's, the fancier the conference centre, the more likely it is not to give you a computer so that you can actually run your own presentation, and then you're dependent on technology. Thanks, Reinhard. It's wonderful to be in Vienna, and wow, beautiful setting. I actually sort of slightly felt like a refugee from the future, and I'm not talking about Brexit, but I realised the title that I'd originally got really belonged in the session before, so the session this afternoon, and so after consulting with colleagues, I thought I would move to something which may actually be a refugee from yesterday's session, thinking slightly more about market design, because a lot of people are talking about the impact of lots and lots of capacity with no costs, or actually we haven't invented the free lunch. You paid for it in the registration fee, and so actually it's a market with a market with marginal costs of zero. Okay, that's it's on now, which always helps. Okay, so yeah, we've got zero marginal costs. Now, by now, we've often seen this sort of graph and supply, demand, prices, which reflect the marginal cost. And we also know the screening curve of fixed and marginal costs, and you can tell which type of plant is cheapest, and then you can build plant to meet, so that if the plant is running, or if you build the right mix of plant for your load duration curve, every type of plant is running for the number of hours for which it's cheapest. And furthermore, if those plants are setting prices at their marginal costs, and if we have some very high peak prices, then the revenues happen to match everybody's costs, and everything is wonderful. And indeed, you can see something roughly like that happening in practice. The price of gas and adjusted for efficiency and carbon, and the price of electricity in Great Britain seem to be moving roughly in step, give or take. This is econometrics, not econometrics, but it's pretty decent fit. Of course, in the UK, we do have another fuel, coal, which actually for quite a period was rather cheaper. This is actually because of shale coal. Ben was talking a lot about shale gas. Shale coal may be less familiar to you. It's normal coal, but it's the coal that the Americans don't want to burn anymore, so they ship it over to us, and it gets cheap. The United States is emitting less carbon than it has for a long time, but it's still digging more carbon out of the ground, I think, than it ever has. Certainly last time I checked the data a couple of years back, it was digging more carbon, it was just exporting a bit more of it, or perhaps importing less. So that's things seeming to work in Great Britain, and if I look somewhere else, apologies, I should actually give credit where credit is due, because I believe you have the same market. And again, it seems to be working, or it was, and then something seems to have gone wrong. Electricity has got a lot cheaper than gas. And if we see what's happening, well, lots and lots of wind and solar capacity, and actually perhaps I should give blame where blame is due. This is the German wind and solar capacity, and it seems to have gone very bad. Yeah, the divergence seems to have started by the time you get to about 50% renewable capacity, which is actually roughly where Great Britain is at the moment, comparing our renewable capacity to peak demand. So maybe we're due for a shock sometime soon. And that is basically due to, if you think about renewables in a power market, and I want to stress power,